The pure solvent in a solution has certain properties. If you dissolve a solute in that solvent, you change those properties. Those properties depend on the number of solute particles that dissolve in the solvent. Uh, this includes what's called vapor pressure lowering, boiling point elevation, freezing point depression, and osmotic pressure. So all four of these things depend on not what kind of solute is dissolving in the solution, but how much, and specifically how many particles. So vapor pressure, as we know, is how much of the solvent is escaping into the gas phase. Well, if all of a sudden I add a bunch of non-volatile is the operative word here. We don't want a solute that has a vapor pressure of its own. That's a whole nother problem. We just want a non-volatile solute, something like sodium chloride. So having no vapor pressure. So when you put the non-volatile solute into the solvent, you're occupying surface sites. And that's going to lower the opportunity for the solvent particles to escape into the gas phase. And that's going to lower the vapor pressure. Less particles going into the gas phase. So the little red dots represent sodium ions, chloride ions. Again, it doesn't matter what they are. All that matters is that they're non-volatile. So if they're sitting on surface sites, they limit opportunity for solvent particles, which are volatile, to escape. And you lower the vapor pressure, less opportunity to get into the gas phase, not decreasing the rate at which they can return. So this is a plot of vapor pressure versus the mole fraction of the solvent in solution, right? So mannitol represents a non-volatile solute. As I increase the mole fraction of the mannitol, I decrease the vapor pressure until eventually, right, if we were 100% mannitol, we'd have no vapor pressure. So this is how it works. It's called Rayleigh law. Vapor pressure of the solution is proportional to the mole fraction of the solvent in the solution. So if I know how many moles of solvent I have, divide it by total moles, multiply by what the pure vapor pressure would be of the solvent, right? That's its P naught there. You get the adjusted vapor pressure, the vapor pressure for the solution. Rayleigh's law is an equation for a straight line, right? So if I plot the vapor pressure of the solution versus the mole fraction of the solvent, the slope of the line is going to be equal to the pure vapor pressure. So it's the graph we just showed before, right? So if you're starting with 100% solvent, no non-volatile solute, you have, 100% vapor pressure, right, in terms of what that solvent would produce at a particular temperature. But as you decrease the mole fraction of the solvent, you decrease the vapor pressure. So calculate the vapor pressure of a solution where you've got 0.25 moles of sucrose and 1.1 moles of water at 50 degrees Celsius. They have to tell me what the vapor pressure of pure water is at 50 degrees Celsius. It's 92.5 torr. All right, so what I need to get is the mole fraction of the water, right? Moles of water divided by total moles. So add up the moles of the solute and the moles of the water, divided into moles of the water. I have a solution that's almost 82% water, so 0.815 fraction of the water. So multiply a fraction by a number and you're going to lower the number, right? So multiply the fraction by the pure vapor pressure, which was 92.5 torr, and I end up with the adjusted vapor pressure being lowered. My puppy's having nightmares in the background here. Okay. 20 grams of urea to 125 grams of water at 25 degrees Celsius. All right, so urea would have no vapor pressure, right? So we're lowering the vapor pressure of the water. They tell me what the vapor pressure of the water is at 25 degrees Celsius. And they tell me what the vapor pressure of the solution is. Oh, okay, so different, right? So if I know what the vapor pressure of the solution is, and I know what the pure vapor pressure would be, what I'm able to get out of that is the mole fraction of the water. Moles of water divided by total moles. So if I know how many grams of urea I had and how many grams of water I had, right, I can use the molar mass of water as a conversion factor to get to moles of water. And from that, I'm able to figure out how many moles of urea I would have, right? So it's moles of water plus moles of urea divided into moles of urea, and we figured out what the mole fraction of the solution was by using the vapor pressure of the solution and the pure vapor pressure. So solve for moles of urea. I know how many grams of urea I had. They told me I had 20 grams, so I can get what the molar mass of urea is. Moles of urea divided into grams of urea gives me grams per mole. So if you're making it harder to go for the solvent to go into the gas phase, right, you're lowering the vapor pressure, that means you're elevating the boiling point. You're making it harder to boil. In addition to this, you're also depressing the freezing point, making it harder to freeze. So frankly, you're increasing the liquid phase in both directions. So it's the same concept. If you have these solute particles at the surface, you're making it harder for the particles to get into the gas phase. So you'd have to get the temperature higher in order to boil the water. So this is the whole reason we add salt to water when we're boiling spaghetti, right? What you're doing is making the water harder to boil. Water won't boil at 100 degrees anymore if you put a bunch of salt in it. Now all of a sudden it's going to boil at 110 or 120, and it's better for cooking, right? You'll cook your spaghetti better, get it hotter. So like I say, you're increasing the liquid phase in both directions. So add salt to the water, you're elevating the boiling point. You have a new phase boundary now at a higher temperature. You're also interfering with the ability of the liquid to go into the solid phase. So you're depressing the freezing point. This is the whole reason for putting salt on the sidewalk. You know, my kids, when I put salt on the sidewalk, they're like, oh, the salt is melting the ice. It's like, no, what it's really doing is making it harder for the ice to go into the solid phase. So you're making the salt water is harder to freeze than pure water. So you're freezing at a lower temperature now. So that's why we put salt on our walks in the wintertime, to keep it from being iced over. Make the liquid stay a liquid longer. Harder to freeze. So boiling point elevation is proportional to the molality of the solution, right? So there's that, concentration unit, molality. So we use mole fraction with vapor pressure lowering. We're using molality with boiling point elevation. So you need some constant in order to equate the boiling point to the molality of the solution and the change in the temperature, right? We're increasing the temperature at which it boils, right? So we're raising, that's the delta T part, we're raising the boiling point by how much will be equal to delta T. So boiling point elevation constant multiplied by the molality of the solution, moles of solute per kilogram of solvent. All right, when the vapor pressure of the liquid is equal to the surrounding atmosphere, you boil, right? So if all of a sudden I have solute particles interfering with that interface, it's harder to boil. You raise the boiling point. Need more kinetic energy in order to escape. So you got to get the water hotter if you want to reestablish that equilibrium where you've got the vapor pressure equal to the atmospheric pressure. Freezing point depression works the same way. The molality of the solution is directly proportional to how much you're changing the freezing point. So again, we need some sort of constant to equate freezing point to the molality of the solution. And specifically, right, the solute. So it's going to be the molality of the solute multiplied by K is going to be equal to how much you're depressing the freezing point. So again, you're interfering with the ability of the liquid particles to go into the solid phase, but you're not interfering with the solid phase going to the liquid phase. So you establish a new freezing point at a lower temperature. You want the particles to go into the solid phase, you have to get them colder now. All right, so this would be a typical problem. Calculate the boiling point of a solution where you've got 0.015 moles of non-volatile anthracene and 45 grams of toluene. The normal boiling point for toluene is 110.63 degrees Celsius. So they gave me what the Kb value was. They gave me what the moles of the solute were. And what I need to get is kilograms of the solvent, right? So convert grams of toluene to kilograms of toluene, 1,000 grams per kilogram, and then divide it into moles of anthracene, and I get the molality of the solution. Multiply the molality by the K value, and what I get out of this is how much the temperature has changed, right? So moles cancel, kilograms cancel. I'm left with degrees Celsius, right? So that's with the constant, right? Degrees Celsius times kilogram divided by mole. Cancel everything except for degrees Celsius. So now all of a sudden, it doesn't boil at 110.63. It boils at 110.63 plus 101 degrees Celsius. You've elevated the boiling point. Depressing the freezing point. Calculate the freezing point of a solution where you've got 0.047 moles of lactose and 25 grams of sugar. So what I need is the molality of the solution, right? Moles of lactose divided by kilograms of water. So again, convert from grams of water to kilograms of water. Divide into moles of lactose, and I get the molality. Multiply the molality by the Kf value for water, right? And they have to give you this, right? So degrees Celsius times kilograms per mole. Everything cancels except for degrees Celsius. And what I get out of this with, let me go back, sorry. What I get out of this with delta T is, again, how much I'm depressing the freezing point. So water usually freezes at 0 degrees Celsius. Well, now it freezes lower than 0 degrees Celsius, right? It freezes at minus 3.5 degrees Celsius by putting sugar on your sidewalk. So here are some boiling point and freezing point depression constants, right? Kb values and Kf values for water, benzene, ethanol, carbon tetrachloride, and so on. So they have to give you these in the problem. They have to have what the Kb value or the Kf value is in order to equate molality to change in freezing point or boiling point. All right, the last colligative property is osmotic pressure. Osmotic pressure is defined by solvent particles moving across a semi-permeable membrane. You might remember the term semi-permeable membrane from biology, right? Certain particles are allowed to go across and certain particles aren't allowed to go across. So with osmosis, right, osmotic pressure, the solvent is water. Water is allowed to go across the semi-permeable membrane, but not the solute particles. So again, you're interfering with that interface between being able to go across the semi-permeable membrane and having access to it. So the pressure required to stop osmosis, right? So once I get a certain number of a rate going across one way and the semi-permeable membrane and the rate equal going in the other direction, the flow of solvent particles across the semi-permeable membrane stops. All right, so pi is the symbol for osmotic pressure. It's directly proportional to the molarity of the solution times RT, and R is the gas constant, right? In what is it? Liter atmosphere mole K. So I got to have my temperature in Kelvin, just like with the gas law. If I'm going to use R, and the concentrations in moles per liter. So this is what it looks like, right? So on the one side of my semi-permeable membrane, I put particles that aren't allowed to pass. So again, right, the solute particles are obstructing solvent particles from having access to the semipermeable membrane. So you're stopping flow in one direction, but you're not hindering flow in the other direction. So you start building up a pressure on the one side. And eventually the rate of going in one direction is equal to the rate going in the other, right, at this new adjusted pressure. So semipermeable membrane, you put the solute particles in, you obstruct in a particular direction, and eventually you build up a pressure, stopping the flow of particles in one direction and making it equal to the flow in the other direction. All right, look at this problem. We've got 1 times 10 to the minus 3 grams of a protein dissolved in 1 milliliter of water. The osmotic pressure of the solution was found to be 1.12 torr at 25 degrees Celsius. All right, so we have a temperature, we've got an osmotic pressure. What we can solve for that is the molarity of the solution, right, moles per liter. So I can rearrange pi is equal to MRT by dividing both sides by RT. So I can solve for the molarity of the solution. If I got moles per liter and they're giving me a density of, oh, there it is, density, grams per liter, we can use that conversion factor to go to grams per mole. So first things first, right? Get your units the same, right? So they gave me the osmotic pressure in torr, 760 torr for every atmosphere. So I have to have it in atmospheres if I'm going to use R. R is 0.0821 liter atmosphere mole K. Got to have my temperature in Kelvin, so add 273 to 25 degrees Celsius. And divide atmospheres by liter atmosphere mole K, and I get moles per liter. So I got the molarity. Multiply the molarity of the solution by the density, and I will cancel liters, and I'll have how many grams per mole I have. So for every 1 gram, I have this many moles. I get the molar mass of this mystery protein.